Hello viewers, in this video we will discuss how we can develop a physics-informed machine learning model. A physics-informed machine learning is an emerging approach that combines principles from physics-based modeling and traditional machine learning techniques. It aims to leverage the strengths of both approaches to improve the accuracy and efficiency of predictions, especially in scenarios where limited data is available. The traditional machine learning models, such as neural networks, are data-driven and can be powerful for pattern recognition and complex function approximation. However, they often require large amounts of labeled data for training, which can be challenging to obtain in many scientific and engineering applications. On the other hand, physics-based models are rooted in fundamental physical laws and principles. They are designed to describe the underlying mechanisms governing a system's behavior and can provide valuable insights into the problem at hand. However, physics-based models may involve simplifying assumptions or lack the flexibility to handle complex real-world scenarios accurately. PIML seeks to address the limitations of both approaches by incorporating known physical laws or constraints into machine learning algorithms. By doing so, PIML can effectively guide the learning process and improve the generalization of machine learning models, especially when data is scarce. This approach can lead to more robust and interpretable models, as they inherently abide by the governing laws of the system. There are several ways to incorporate physics into machine learning models. Let's see and try to understand them individually. The very first type of physics-informed machine learning is data augmentation, which is also known as observational bias physics-informed machine learning. In this type of PIML, we generate synthetic datasets to train the machine learning model. This means we need to generate additional training data by perturbing the existing data using physics-based constraints. This allows the model to learn from physically consistent variations. For example, instead of using real data as input features, we will generate some synthetic datasets from a physical model or simulation and use them as input features to train the model. The second type of physics-informed machine learning is loss function regularization. In this type, we modify the loss function used during training to include terms that penalize deviations from known physical principles. For example, in structural health monitoring, we aim to detect and predict structural damages in buildings or bridges. We have limited sensor data, and traditional machine learning models may struggle to generalize well. However, we can incorporate physics knowledge about the material properties and behavior of the structure into the loss function during training. By penalizing predictions that violate the known physical principles, e.g., stress-strain relationships, the model can learn to respect the underlying physics and make more accurate damage predictions. The third type of physics-informed machine learning is hybrid modeling, in which we need to combine physics-based models and machine learning models to create a unified framework. For example, climate models based on first principles are computationally expensive and may not capture fine-grained details. On the other hand, machine learning models can be more computationally efficient but might lack physical interpretability. In this case, a hybrid model can be used. The physics-based model simulates the large-scale climate patterns, while a machine learning model fine-tunes the results to capture regional nuances or correct biases in the simulation data. This hybrid approach combines the strengths of both models for improved climate predictions. The last type of physics-informed machine learning is model structure and architecture, in which the design of the architecture of the machine learning model is done in such a way that it adheres to known physical properties or invariants. For example, when predicting material properties, e.g., conductivity, strength, using machine learning, we can design the architecture of the model to incorporate known physical principles. For instance, we might use convolutional neural networks for analyzing crystal structures, where the convolutional filters are designed to detect repeating patterns corresponding to the crystal lattice. This approach ensures that the model adheres to the inherent symmetries and properties of the material's crystal structure, leading to more physically meaningful predictions. Remember that the effectiveness of each approach depends on the specific problem and the quality of the available data. Physics-informed machine learning is a flexible framework, and researchers and engineers should carefully consider how to best integrate domain knowledge to tackle the challenges in their respective fields. That's all for now. Thank you for watching. If you enjoyed this video, please give it a thumbs up and consider subscribing to the channel for more content.